encoding, and last I will conclude with the BERT model. The reason why I'm discussing all these things is because your LLMs, whichever LLM you take nowadays, it is using this kind of architecture, that is the BERT architecture by LSTM, etc. So that's the reason why I'm discussing these basic topics, so that at least you know what LLMs are using behind the scenes. So let me start off my lecture, as I said, with the introduction to recurrent neural networks. So these are the topics that I would be discussing: the motivation behind RNN, then describing the basic architecture of an RNN unit, then how RNN calculates the loss, that is RNN feed forward pass, then various applications, then advantages and disadvantages of a plain RNN, then how these disadvantages are overcome using long short-term memories, and how they work. So that's the first part of the lecture. So now first let us discuss about what is the motivating factor behind RNN, that is why do we require RNN. So the first point that I would like to bring forth is RNNs, they belong to a category called as sequence models, in the sense like where you have applications containing sequences like time series prediction, stock market prediction, interpretation of a language, that is machine translation, then identifying the sentiment of a particular phrase or a sentence. So in all these applications, if you notice one thing, the common thing is they are all in a sequence. Okay, they are all in a sequence form. So all such applications are called as sequence-based applications, and the machine learning models that deal with these sequence applications are called as sequence models. And RNN actually helps us deal with such kind of applications. Okay, and coming to the major description of RNN, like why we require it is because for a normal artificial neural network, you would be having a fixed length input and a fixed length output. But in some applications, there are situations where you would be having different lengths of input and maybe one or two binary outputs. Okay, so that is, not all programs can be converted into one fixed length of inputs and fixed length of outputs, because the inputs and the output lengths are varying. And as we proceed further in the lecture, you will be understanding what this point means. And coming to the next point, problems such as speech recognition, time series prediction, all these, they require a neural network to store the previous information. Okay, to store the previous information, or in fact, if I want to perform a sentiment analysis, an application called as sentiment analysis, I need to actually remember the entire context, like store the information regarding the entire context. What are we trying to talk about in the context? Okay, so normal ANN doesn't have this feature of storing information. That is, it doesn't have a component called as memory. Okay, so that is one aspect. And the other aspect is a normal ANN works in terms of iterations or epochs. Okay, we do not train a ANN based on time. There are situations where we will be talking, or we will be training models or applications in terms of time. So it is hard or impossible to choose a fixed context window. That is, a fixed context time frame. Okay. So for keeping in mind all these points, that is, you don't have a fixed length input output uh, outputs, and then you don't have a memory component in the neural network, and then you also don't have you're not training the neural network based on the time stamps or the time period. So keeping all these things in view, and then a normal artificial neural network only deals with a feed forward neural network and back propagates the error. So, and the other important aspect is the hidden layers, they don't share information among each other. The hidden layers, they don't share the weights among each other. So keeping all these points in mind, they have the researchers have been motivated to develop the recurrent neural network, which addresses all these problems which a normal neural network has. Okay, so let's see like how these problems will be dealt using a RNN. But then before seeing how they will be dealt, we first need to know how RNN architecture is formed. So for our device RNN, the main thing that we need to do is RNN mainly takes the previous output or the hidden states as input. Okay, this point I won't be elaborating now. I'll explain it via the architecture. All you need to remember is RNN takes the previous input from the node, from the previous node, as the current input, previous output of the previous node as the current input to the current node. Okay, previous output from the previous layer as the current input to the input layer. And the other thing is, as I mentioned in the previous slide, RNN trains over time. RNN trains over time. The reason time is involved is because we want to add the component of memory. Okay, we are adding the component of memory. So the point here says that the composite input at time t has some historical information about the previous timestamps. Okay, so at the current timestamp t, okay, you would be having the previous information or the previous historical information, whatever happened, that is of all the time period capital T. Fine. Then the third part is RNNs are useful as their intermediate values can store information about past inputs. Okay. So let's see how these three things, like how do the RNN store input? That is one. Then how does the RNN take the previous output as the current input? And how is it trained, or how is the information or the context information stored for a particular period of time? So this is the basic architecture. And this architecture that you're seeing here is the architecture of a single RNN unit. Please remember, it is the architecture of a single RNN unit. Here, T indicates timestamp or a time instant. And we say that when T is equal to 1, the input that is going into the unit is called as X1. Okay. So on X1, we apply some function, we give some weights. Okay, some processing happens and then it goes to H1. And then from H1, we apply some activation function and then we generate some output and get Y1. So X1 here is the input. H1 is the what they call hidden layer input, and Y1 happens to be the output from the output unit. Okay, all this is at T equal to 1. So this is your basic RNN cell structure. Now, if I just remind you, just look at this first point. It says RNN takes the previous output or hidden states as current input. Let's see how that is done in the architecture. So at time t equal to 2, again we have x2, h2, x2 going into h2. But if you notice, there is some additional link that we have added. That is the output from H1. The output from H1 is added to H2. The output from H1 is added to H2. So the inputs that H2 is getting are one from X2 and the other one from H1. So there are two inputs H2 is receiving. What are they? One is from H1, which is H1's output, that is previous state's output. Okay. Along with the current input, both of them are going into H2. Okay. And some processing happens here and we are getting our Y2. The same goes on till t equal to 3, x3. H3 takes input from H2 and uses it for generating Y3. So all these three are RNN single unit cells. They are single unit cells. And this is called as unfolding of RNN. This is called as unfolding or unrolling of RNN. So if you remember in C programming or in C++, I mean, that is the basic for programming languages that we have learned. In that we learned about iterative loop, something called as a for loop. In case of for loop, if we just take one simple iteration, I write it as for I equal to 0, I less than n, I plus plus, okay. And then I implement some operation inside the for loop. If you notice at one particular iteration, the value of I will be 1. At another iteration, I value will change to 2. I mean, it will keep on increasing till n, right? So, but then one thing that is constant, although the value of I is changing, one thing that is constant is the variable name I and the memory address where I is stored. The memory address where I is stored. So those two things are constant. The only thing that is changing is the value inside the memory address. The value inside the memory address based on each iteration. The same logic applies for your RNN as well. Okay. All these cells are actually combined into one, but then they expand as the time unfolds. They expand as the time unfolds. At each iteration, you would be giving one input at a time. You would be generating one hidden output at a time. That hidden output will be given, will be processed, and you would be generating one output Y1 or Y2 or Y3, etc. at that particular time instant. This is what we call as unrolling or unfolding of a RNN neural network. Now, the other thing is coming to the t equal to 1. The previous output is H0. H0 happens to be an initial state. H0 happens to be an initial value that we are feeding into H1. Because the architecture itself says that from previous states, we are taking the output and feeding it as the input to the current state. So H0 would be taken as some random initial value. Okay. So this is how your RNN architecture looks like. A single RNN cell to the unfolding of various RNN cells. And that is what we have said in the first slide. RNN neural networks, they take the previous output, which was H0 to H1, H1 to H2, H2 to H3, etc. Okay. And the composite input at time t, it has some historical information, and they use RNNs use intermediate values. We'll deal with this when we talk about LSTMs in particular. Okay. So the first point is clear, I hope so. Let's deal with, let's see what is the activation function. Now your vanilla RNN cell, that is the basic RNN cell, it takes the TANH function as the activation function. We all know that there are many activation functions like sigmoid function, ReLU activation function, then you have softmax function, then other function is your TANH function. TANH function gives you a value between -1 and +1. And what they call TANH is mainly used for giving importance to a particular importance. Okay, it gives importance to the words. +1 meaning highly important, -1 meaning less important. Okay, so your HT, the activation function at HT, is a TANH function which takes input xt with some weight vector w and the previous state's output ht minus 1. Okay, so this is your basic activation function. Please remember, this is your basic activation function which is used at HT. Unfortunately, using only this activation function, that is using only TANH function, will not suffice, okay, for complex applications like text analytics. We'll see how what are the other activation functions we can add, but a bit later on. Now, coming to the vanilla RNN feed forward network. So this feed forward network, it mainly talks about the loss function. If you notice here, for at time t equal to 1, x1 is the input, h0 is the input. You apply TANH function, perform some operations, get y1 as an output, and check if the output is correctly matching the target output or not. That is, the generated y1 should match the target output. If they don't match each other, then that indicates a loss, which is given by C1. So here, C1, C2, C3 basically are nothing but the loss functions associated with each RNN unit. Okay, that loss function can be anything. If we are using softmax function, it will be cross entropy. So like that, if you are using binary, then it will be a normal loss function, mean square error function, etc. Okay, and these blue lines are nothing but H1's output going as input into our RNN cell number 2. Along with this, okay, we have one more component that we are supposed to add, and that is this. These yellow, blue, green lines, all these solid lines, they indicate sharing of weights. They indicate sharing of weights. That means information is being shared among all the RNN cells. This is a major advantage of using deep learning neural networks. Even in CNN, you have this concept of shared weights. Okay. The reason why we do this is because each hidden layer needs to send its information to the rest of the hidden layers. So that's why we have this solid connection. That means there would be a connection between all the hidden units and all the input units. Okay, this is called as sharing of weights. This is an important part because based on this only we will be performing sequence modeling. Okay, so this is your basic architecture of how a RNN looks. C1, C2, C3, as I mentioned, they are the losses which need to be calculated, evaluated. And as I mentioned earlier also, these individual units, okay, they are called as unfolding of network through time, okay. But at one particular time instant, it will be one RNN cell, okay. And you can fold it all together. It's simple like a Chinese or Japanese paper fan. You fold it, you fold all of them together, you expand all of them together. That's called as unfolding and folding or unrolling network through time by making copies at each time step. Okay, by making copies at each time step. So now, as we mentioned, the RNNs, they share weights over time. They share weights over time, and then they also make copies of the RNN cell. That is called as unrolling or unfolding with different inputs at different time steps. Please remember the for loop. That's quite enough for understanding unrolling or unfolding for this particular concept. Okay. So these 2 points are quite important. They are sharing the information, that is the weights across time, and making multiple copies across various time steps. Now, let's talk about the applications. Applications are mainly dealt in terms of input-output scenarios. That means if we have a single input and a single output, that means a single X and you get a single Y, okay, then that is called as a feed-forward network. If you have single and multiple outputs, like for example, you feed in an image and then you try to describe that image in a sentence, in the form of a sentence or in the form of a phrase, it is called as image captioning. Okay, where these each multiple cells that you're seeing will generate each and every word in that sentence. Next, multiple to single. Here you have multiple inputs, but you are generating a single output. Now, last is multiple to multiple. Multiple inputs and multiple outputs. Example is machine translation and also image captioning. Okay. Now, the main important thing here is that based on the application in hand, your architecture will change. Based on the application in hand, your architecture will change. Like for example, if you want to do machine translation, you are supposed to use multiple to multiple. Okay. And if you just want to do what they call sentiment analysis, then you would be using multiple to single. Okay, so whatever application you have in hand, based on that, you would be taking the input-output scenarios. Okay, so now let's see examples for these input-output scenarios. The first is sentiment classification. Examples are like if you have to classify or review a restaurant from some Yelp app or movie review based on IMDb scores, or just say if a sentence is positive or negative, then the inputs would be multiple words or maybe one or two sentences, but the output might be only just positive and negative classification, either yes or either a no. Some examples for this are the food was really good. Okay, now can you tell me if this sentence is a positive or a negative classification? Is this positive or negative?
This is positive sentence.
Okay. How are you able to tell that it's a positive sentence?
The word good is exist in this sentence.
Okay, fine. Then the next sentence is the chicken crossed the road because it was uncooked. Now, can any of you infer if it is a positive or a negative class?
It seems negative, ma'am.
Okay, the reason being it was uncooked.
Yes, ma'am.
I can also say it is a positive. The chicken escaped.
Yeah, I think it is ambiguous.
It is actually ambiguous. That means there is something which is a big challenge in natural language processing, and that challenge is nothing but ambiguity. There are different types of ambiguity actually. Unfortunately, since this sentence does not have extra information with it, we can't really classify it to be positive or a negative sentiment. Okay. So these are some of the examples where we really can't work well. Okay. We require some additional information, and we'll see how we can give some additional information and tackle this problem. So first of all, let us concentrate on this positive sentence. That is, the food was really good. So this is how it works. The and then the food, everything is given into an RNN. Okay, and some processing happens, and ultimately, based on all the words, we would be checking if it is a positive or a negative class. But then, as you some of you just now mentioned, we don't really require all the words in this sentence, right? That is, we don't require the words the, food, was, okay. Those three words we can just ignore, right? We can just ignore those three words, the, food, and was. We can only concentrate on, or we can take important information from the words really and good. So once we take only the important words in the sentence, okay, once we take only the important words in the sentence, we feed them into the classifier and say whether it is a positive or a negative class. Okay, so that is, you give weightage to each and every word. Okay, the ones which are supposed to be ignored will have less weightage. The ones which need to be given more importance will be having more weightage. All of them together are summed up, combined, and then you get your linear classifier, whether it is a positive or a negative class. So this is how your sentiment classification works. That is by ignoring some words. Now, how this ignoring works, I'll show you when I deal with LSTM. Now, coming to the other application, this is image captioning. Given an image, you produce a sentence describing its contents. So inputs are nothing but image features which we extract using CNN, and then the outputs are multiple words. Okay, that is something to build a sentence. Okay, so here if you notice the dog is hiding, that is how it is given. For image captioning, the first and foremost is, as we mentioned, we require an image. That image is processed or trained, or the objects in that image are identified using CNN. Fine. Once the objects are identified, those words are fed into the RNN. Okay. And then your RNN will be able to give you the correct output. That is, the dog is hiding, etc. A lot of processing goes into this complex operation, but looking at the architecture, it seems quite trivial. And these are some of the examples of image captioning. A group of young people playing a game of frisbee, a close-up of a cat laying on a couch. Okay. So now coming to the advantages and disadvantages. We have seen some of the applications where RNNs are used. So keeping those applications in mind, we are saying that RNN remembers each and every information through time. Okay. And hence it's useful in time series or to stock market prediction. And this is called as long short-term memory. That is, uh, remembering the previous context, okay, and then trying to give the current output. That is called as long short-term memory. And the recurrent neural networks are even used with convolution neural networks for image captioning. Now, coming to the disadvantages, there are mainly three disadvantages. One, the gradient vanishing and exploding problem. Then training an RNN is a very difficult task, as I just now mentioned, because using a normal tanh function, you will not be able to perform all the applications or implement all the applications. So it cannot process very long sequences if using tanh or ReLU as activation functions. Okay. So let's see what are these disadvantages and how they can be tackled. The first is your gradient vanishing and exploding problem. Like, what exactly do you mean by the vanishing gradient problem or gradient vanishing problem? So when we train a RNN, okay, your slope can either be too small or otherwise it can be too large. Fine. And this makes the training very difficult. Okay. And when the slope is too small, then it is called as your vanishing gradient problem. I'll give you a simple example. I guess all of you might be already knowing about backpropagation neural network, because I mean this workshop mainly deals with advanced concepts, right? So I believe that you might be knowing what a backpropagation algorithm does. In case of your backpropagation algorithm, what happens is when your target output and your generated output, if they don't match, you calculate something called as an error, right? And that error or the loss is actually fed back inside the neural network. It is fed inside the neural network in the backward direction. And that is the reason why it is called as your back propagation neural network. Fine. Now, when this error is back propagated, what we intend to do is we intend to change the value of the weights. We intend to change the value or update the weights, right? For each network, that is for each layer, sorry, or in case of each layer, all the weights are updated as the error back propagates. Now, in case of long sequences, in case of long sentences, like for example, okay, there might be situations, okay, there might be situations where the error, while it is back propagating, almost becomes zero. By the time it reaches the input layer, okay, the error might become almost zero. Fine. So in such case, when the error becomes zero, what will the input layer do? It will do nothing. It will not update its weights. The reason being that there is no change. Error is zero. That means you don't need to change the weights, or you do not require any updation in weights. Hence, the weights will remain the same. But unfortunately, the target output and the generated output are still not the same. That means you still need to update the weights. Okay. This problem usually happens when you have long sequences. And when the error becomes almost zero, it is called as the vanishing gradient. Okay, it is called as your vanishing gradient. We'll look at one example and then you'll understand it much better. Now, the opposite to this is your exploding gradient problem. That is when the slope tends to grow exponentially instead of decaying. The problem is exploding gradient. I mean, the error keeps increasing. Okay. And the issues with this vanishing or this exploding gradient are long training time, poor performance and bad accuracy. Okay. Let's see some examples. Consider the following two examples. One is the person who took my bike, okay, and some words. Let me say the person who took my bike and fled dash a thief. So the task is you need to fill the word inside this dash. You need to fill the word inside the dash. Fine. The sentence reads like the person who took my bike and fled dash a thief. Now the next sentence is the students who got into engineering with MPC as their group, okay, with maths, physics, chemistry as their group, dash from Asia. So again, you need to fill the word inside the dash. So there are luckily you only have two options here. One is you fill either the sentence with was or either you fill it up with were. But in order to fill the sentence with was or were, okay, you need to find whether the subject is a singular noun or whether it is a plural noun. That is, in order to understand what would be the next word in the sequence, your RNN must memorize the previous context. That means fled, and, bike, my, took, who, person, the. All this information needs to be stored inside your RNN. In this, the main important subject is person, right? So we need to check if it is a singular noun or if it is a plural noun. Fine. While going back in this direction, there is a chance that RNN forgets. There is a chance that RNN will forget. That means RNN might face vanishing gradient problem. Okay. So if you notice, you have ST, you're going back S3, S2, S1. But unfortunately, by the time it reaches S1, your gradient almost becomes zero. And then you will not be able to fill this word here. Okay. So same goes with the second sentence also. So maths, physics, chemistry, with engineering, into, got, who, students. Still students we need to memorize. Fine. So it might be sometimes difficult for the error to back propagate to the beginning of the sentence, okay, in order to predict the actual output, Fine. So these are the main problems that your RNN has. That means the vanishing gradient problem. Now, what are the solutions to this gradient problem? If we talk about exploding gradient, then you can clip the gradient. That means till certain time, till certain decimal value, you can just clip it. That's one easy way of doing it. Then the other, for vanishing gradient problem, the solution that we have at hand are long short-term memory networks. That means if you have long sequences, that's when your vanishing gradient problem is occurring, correct? So you can't just clip your sentences into two halves, or maybe cut the sentences into chunks or bits and pieces for performing the back propagation, right? You have to sometimes deal with long sentences. So when you have these long sentences, to deal with them, we use something called as LSTMs. But in order to understand LSTMs, we first need to understand what exactly are long short-term memory. So let's deal with now the long short-term memory or long-term dependencies. So suppose if we have a sentence like the clouds are in the dash. So the ideal word for this sentence is sky, right? I mean, of course, you don't need to wreck your brains over it. The clouds are always in the sky. They are not in our brain, correct? So we do not need any further context, or we don't require any more information. It's pretty much clear that the word is sky. But suppose if we try to predict the last word in the text is, I have been staying in Spain for the last 10 years. Okay. I can speak fluent dash. So the last word, logically, it needs to be filled with the word Spanish. But if you want to predict this last word Spanish, we actually need to back propagate till the word Spain. Okay, that is, we require the context of Spain in order to predict the last word in the text. And because we are back propagating, it's a long sequence, it's possible that the gap between the relevant information and the point where it is needed becomes very large. Okay. These are called as your long-term dependencies. Okay. And to address this, we use LSTMs, long short-term memory units. So now let's take or see how LSTM works. To begin with, LSTMs are the sub-architecture or an advanced architecture of a recurrent neural network. Okay. They are capable of learning long-term dependencies. Okay. And they are capable of storing information for longer periods of time. Unfortunately, RNNs, plain RNNs or vanilla RNNs, they didn't have that. But LSTM has this advantage of storing information for longer period of time. Okay. Now, in case of your vanilla RNN, as I mentioned in the beginning of the class, the activation function used was tan H function. But there are little modifications or little additions made to LSTMs. Along with your tan H function, we have added 3 more activation functions. We have added 3 more what we call it as interacting layers. Okay. Along with the tan-h function, we have added the 3 more interacting layers. Fine. Now, these layers are added in between, inside your hidden unit, where the entire processing takes place. I mean, HT minus 1 along with XT is fed into HT, where the processing takes place, right? Now, let's see what these interacting layers are. When it is combined with tan-h, of course, there are 4 interacting layers. Okay. Let's see one by one. Your LSTMs, okay, they work in 3 steps. They work in 3 steps. And in those 3 steps itself, those 4 interacting layers are used. The first is called as your forget gate, which forgets irrelevant parts of the previous state. Okay. And the second is called as input gate, which selectively updates cell values, cell state values. And the last one is output gate, which outputs certain parts of the cell state. Now, one important change here is that in case of the previous slide, we said HT minus 1, HT, etc. Now we have subdivided them into cells. Okay, we have subdivided them into cells. So your HT comprises of cell 1, cell 2, and cell 3. And CT minus 1, which is cell T minus 1, is from the previous cell. Okay, is from the previous unit. Fine. So here CT minus 1, CT, they indicate your individual cells inside your hidden unit. Okay, inside your hidden unit. Now, the first, as I mentioned, is your forget gate, second is your input gate, and the third one is your output gate. So your LSTMs, it works in these 3-step manner. Okay. Let's see how the LSTM works step by step now. So the first is step 1. As I mentioned, it's called as the forget gate. It decides how much of the past it should remember. That is, the first step in LSTM is to decide which information is to be omitted from the cell. Okay, and which information needs to be retained. If you remember, in case of sentiment classification, I had mentioned about a sentence called as the food was really good. And you had already told me that based on really good, we were able to positively classify that sentence. That means we ignore the words the, food, and was. Now, how I also said that we need to ignore. Now, how this is ignored? Using the forget gate. Okay. Ignoring certain words in a sentence is done using the forget gate. That is FT, which is indicated as the variable for, and here what happens is we use a sigmoid function, okay, which words, okay, or which context needs to be what they call remembered, which context needs to be omitted is decided using the sigmoid function, okay, and the sigmoid function, it takes the previous state, that is HT minus 1, and the current input XT, and computes the forget gates output. That is, you take the previous output, which is HT minus 1, you take the current input, which is XT, perform sigmoid operation on them, and then your forget gate will tell you whether which information needs to be omitted and which needs to be retained. Okay, so this is the activation function. BF is nothing but your bias. Okay, forget gate, as I said, decides which information to delete that is not important from the previous time step. So in HT minus 1, the information which is not required, that will be omitted. Please remember, not in the current input. XT तो वैसे ही रहेगा. But HT minus 1 से कितना information मुझे लेना है? Okay, that is decided by your forget gate. Now let's look at one example and see how FT works. So consider an LSTM with the following inputs, okay, with the from the previous and the present timestamp. HT minus 1 ka output, that is previous output, is like this. Alice is good in physics. John, on the other hand, is good in chemistry. So this is the output from HT minus 1. XT is John plays football well. He told me yesterday over phone that he had served as the captain of his college football team. So this is XT and this is HT minus 1. Now combining these two itself, your forget gate will work, but the condition is it will only remove information from HT minus 1. So forget gate realizes there might be a change in context after encountering the first full stop. Okay. So first full stop is encountered here. Forget gate says that the context is changed from Alice to John. That's the first observation. Next. This information is compared with XT. Next. Since XT also talks about John, okay, XT also talks about John, the information regarding Alice is deleted. Fine. So this is how your forget gate works. So the position of the subject is vacated and is assigned to John. Fine. So this is what your forget gate helps us in doing. Like it tries to identify what is the context that we are trying to talk about by omitting and retaining useful information. So this is how your FT works. Now let's look at the second step. Now we have got the information that John is the context that we are trying to understand. So step 2 decides how much should this unit add to the current state. Okay, so that is in the second layer, there are two parts. One is the sigmoid function and the other is the tanh function. In the sigmoid function, it decides which values to let through, 0 or 1. Tanh function gives weightage to those values which are passed inside the gate. That's the reason why it is called as input gate. Okay, if you remember in Ambani's son's marriage recently, I mean few months back, there were VIPs, there were VVIPs, there were VVVIPs, okay. And all of them were given return gifts based on their VIP status, right? So the idea here also is the same. Input gate, it analyzes on XT. It makes its analysis on XT and HT minus 1. But usme bhi, okay. Now we were only talking about what they call. We said that John is the main important thing here, theme of our training. But in this also, based on HT minus 1 and XT, what is the important information that we are supposed to let through? Okay. And what is the other importance? What is the unnecessary information that we can just avoid? These are two steps inside your input gate. That is, determines which information to let through based on its significance in the current time stamp. Okay. So again, as I mentioned, you use two activation functions, sigma and tan H. BI happens to be the bias at the input unit. BC is the bias at the what they call for the weightage function. So consider the input XT, which is John plays football well. He told me yesterday over the phone that he served as the captain of his college football team. So this is your input. Now this input is analyzed by the input gate. And what input gate does, it needs to divide which is VIP, which is VVIP, and which is triple VIP, right? So John plays football and he was the captain of his college team. That is very important. Okay. And he told me over the phone yesterday is less important. Hence, that is forgotten. So that is what your input gate does. Okay. Even after forget gate gets some information, उसमें से भी out of that also, which is important, which is more important, that is what your input gate does. So this process of adding some new information can be done via the input gate. What new information? Abhi tak to we were talking about John, but then the new information that we have added here is he was the captain of his college football team. Okay, so that information extra we have added in the input layer. Now using that information, let's keep it aside. In case of step 3, we have decides what part of the current cell state makes it to the output. Okay. So the third step decides what will be our output. It can be different. You can have what they call complete a sentence. You can predict a word in a sentence. Okay, you can do sentiment analysis. It can be different application. So the third step is to decide what will be our output. First, we run the sigmoid layer, which decides what parts of the cell state make it to the output. Means once you have analyzed your input information and once you know what is the context, uske hisab se you will be trying to give the output. Okay. And what parts of the cell state make it to the output, that is one using sigmoid. Then we put the cell state through the tan H to push the values to between -1 and 1. Okay, and multiply it with the output of the sigmoid because we need to give importance to the words also. This entire thing is called as your output gate. That is, allows the passed in information to impact the output in the current time step. Allows the passed in information to impact the output in the current time step. So let's see how this output gate works. So let's consider an example of predicting the next word in the sentence. What is the sentence? John played tremendously well against the opponent and won for his team. For his contributions, Brave Dash was awarded player of the match. You need to predict the word, that is the blank, okay, inside this sentence. So there could be a lot of choices for the empty space. Can you give me some choices, please? Can you give me some choices? Give me some options for
Captain.
captain or and that's it.
Man of the match, ma'am.
अच्छा. लेकिन one thing is that कैप्टन जो था हमारे पास वो प्रीवियस इनपुट से आया था. I mean we had that previous information कि he was the captain of his football team, right? लेकिन मैन जो है हमें कहीं पे आया नहीं है. We don't know whether man is belonging to female gender or it is male gender because we haven't done any processing on it. Any other options? Any other options?
Footballer.
Sorry, what?
Footballer.
Okay, so we have three. That is क्या था? Brave footballer एक है, brave captain एक है और brave man. Now current input that we are giving, so the current input that we are taking is an adjective. I mean, current input brave is an adjective, and adjectives. The words after adjectives, they are generally your nouns, right? So the what they call
John
the
can be the
best
answer.
noun. Can you switch off your mics, please? The best possible noun that fits this particular sentence is okay. Adjective describes a noun. The best possible noun that describes this sentence is, because we are talking about John previously, and this sentence also talks about John. So the simple noun which fits into this sentence is John. So John could be the best output after brave. Okay. Although you can have what they call words like footballer, you can have words like man, you can have words like captain. But then when you talk about the probability for each of these words, I guess John will be having the highest probability because earlier also entirely we were talking about John. Everywhere we spoke about John. So the best option that your output gate takes is or gives more importance is for the word John compared to other words. So John played tremendously well against the opponent and won for his team. For his contributions, brave John was awarded player of the match. So that's the sensible conclusion for this sentence and the conclusion for the lecture on LSTMs. So I hope you have understood the working of LSTMs and RNNs. Yes, no, nothing, neutral. No.
Yes, ma'am, understood.
Okay, because I mean, these lay the foundation for the next advanced topics that I'm going to deal with. So when you feed this tank into RNN, the word that you need to get is you. Fine. So can we take a 5 minutes break or should I continue? Huh? It's 11:25 now.
Yes, ma'am. We could take a break.
Break.
So I hope the PPT is visible.
Yes, ma'am. It is visible.
Fine. तो अभी के लेक्चर में what we will do is पहले तो we will take why we require encoder decoder models, means why we are shifting from normal RNN, then from LSTM to this encoder decoder. Then we'll talk about what they call attention in these encoder decoder models, that is transformers. Attention, फिर self attention, उसके बाद मल्टी हेड अटेंशन, फिर मल्टी हेड के साथ पोजिशनल एनकोडिंग, और लास्ट में विल बी टॉकिंग अबाउट बर्ट आर्किटेक्चर. सो your problem with traditional RNNs is that they all deal with sequences. Like you can't really have what they call machine translation, summarization, text summarization, question answering, and all that. That really can't work using the traditional RNNs, right? So, I mean, they use that sequence to sequence modeling. So, for applications of translation, question answering, we require models that handle variable length input and output. Okay. And the training also needs to be completed in a very less amount of time. Fine. So for this itself, RNNs, they don't really work. And this is your architecture that we have seen. And so what we do is we resort to an advanced architecture, which is called as your encoder decoder architecture. Okay. Now, in case of applications like machine translation or text summarization, this encoder decoder model really helps us to translate well. Unfortunately, Google Translator doesn't do a great job, but फिर भी कुछ तो ठीक है उसमें. So let's see how this encoder decoder actually works. Your encoder, what it does is it encodes the plain text, that is, reads the entire input sequence and converts it into a fixed length vector, which is called as your context vector. And this fixed length vector, or what they call context vector, is also termed as your word embeddings. They are also called as your word embeddings. That means, I did not mention this in the previous first part of my talk. I just gave you the plain, what they say, the working of the RNN and LSTM. But one thing that I want to mention is that given some plain text, like for say example, English, the words in that English, I mean, the computer cannot understand that plain English language, correct? It needs to be converted into something which the computer can understand. Say, for example, zeros and ones, or maybe some real values. Okay. So the first and foremost thing when you have a plain text, that means a sentence or some words belonging to a particular language, say English, you first need to convert them into a different format which the computer can understand, right? So there are techniques which can do that. So one technique is called as one hot encoding. One hot encoding. So given a particular sentence, what we do is, sorry, let me put it this way. Given some couple of sentences, first what we will do is we will identify all the unique words in that in those sentences. First, what we'll do is we'll identify all the unique words in that sentence, and using those unique words, we'll create something called as vocabulary or a corpus. Okay, so that is the first thing that we do. So जब भी हमारे पास कोई sentences आते हैं, paragraph, phrases वगैरह आते हैं, उसमें से सारे यूनिक वर्ड्स उठा के उसको हम एक वोकैबुलरी करके बनाते हैं. We make it into a vocabulary. And in this vocabulary, how we place the words is based on their alphabetical order and give something called as indexing to each and every word. The reason why I'm telling you all this is because अभी जब मैं coding दिखाऊंगी आपको, तो in the coding I have done all this part. Indexing का part मैंने किया हुआ है, ठीक है? तो अभी मान लो कि हमें एक वर्ड को like identify करना है if it's there in the sentence or not. Okay. So suppose these are the cells indicating each and every word in the sentence. Okay. And suppose I have a word like sentence like the cat sat on the mat. The cat sat on the mat. ये है हमारा sentence. Fine. Now on this sentence, okay, I have to check. Okay, I have to check if a particular word is there inside the sentence or not. So I suppose I pick up a random word, like I have a random word, say cat. Okay, the word that I have selected is cat. If the word cat is present in that sentence, whatever I just now mentioned to you, then that will be indicated by a 1 in its current position. क्या था sentence? The cat sat on the mat. ये था ना sentence. तो जहाँ पे ये cat है, that will be indicated by 1, and rest of the words will all be indicated by 0. This is what we call as one hot encoding or one hot coding. Okay. The presence of a word is indicated by 1. The rest of the words are all indicated by 0. Okay. And this is one technique of encoding a word, means converting a word into a vector form. Now the question here arises, what could be the length of the vector? The length of the vector is usually the length of the vocabulary. तो माने कितने भी words हो vocabulary में. So like for example, if you have 10,000 words in the vocabulary, this vector length that you are seeing here, ये जो vector length है, that length will be 10,000. उसमें से सिर्फ एक ही एक 1 होगा, बाकी के सारे 0 होंगे. So this indirectly makes it into a sparser representation. जब computation करेंगे इसके ऊपर तब मुश्किल हो जाता है because most of them are zeros, right? So to work on such kind of sparser matrix or sparser vectors, it becomes very difficult. Okay, so in order to tackle this problem, like apart from one hot encoding, we also have other techniques like continuous bag of words model, and it is also called as CBOW or skip-gram model. It's also called as word-to-vec model. Okay. Continuous bag of words में क्या होता है कि we have a particular context. ठीक है, context we feed the entire context into the neural network, and we try to predict a certain word in the context. Okay, so we have all the information regarding all the words in the context. So uske hisab se we have to find a certain word. So that is continuous bag of words, or each and every word again is converted into this one hot encoding scheme. Now coming to the skip-gram model, also I mentioned it's called as word-to-vec model. इसमें क्या होता है कि they try to give you not just only encoding, they try to also give you the relationship between words. Skipgram basically says that they give you one word, you try to predict the sentence, or you try to give the entire context. Skip the word, give the context. That's why it's called a skipgram. तो क्या करते हैं कि ये वर्ड उस सेंटेंस में फिट हो रहा है या नहीं. आई मीन दे ट्राई टू चेक इफ द वर्ड हैज एनी कनेक्शन विद द कॉन्टेक्स्ट, अदर कॉन्टेक्स्ट वर्ड्स और नॉट. That's what they try to do in case of this skipgram or word-to-vec. And during this conversion, along with the one-hot encoding or one-hot coding, they also bring out the relationship between the words, like how are the words connected in the sentence? How are the words connected in the sentence? Again, to find that connection, we use something called as co-occurrence matrix. Okay, that's a different thing. We find the cosine similarity between the words. That's a completely different topic altogether. But this embedding or the vector which we get out of word-to-vec, it gives you a relationship. Like, for example, how bread is to butter, we have higher relationship. Okay, bread will not have a relationship with a higher relationship with rice, correct? King will have higher relationship with queen, correct? And the man will have a higher relationship with women. So that ways you give relationship scores and create your vector. Okay. These are now called as, when you have relationships into picture, I mean, how are they connected with the other words in the context? They are now called as word embeddings. So you either can treat one-hot encoding as a word embedding or otherwise you can call the relationships along with one-hot encoding as word embeddings. So your encoder here, my entire idea of talking about all this is that your encoder, when you give a plain word, English word to your encoder, it converts it into this word embedding. But then we don't have the word embedding to be the length of the vocabulary. Earlier we had the length of the vocabulary, right, for one-hot encoder. Now what we do is we fix it to one certain size. Okay, that word embedding is converted into a one fixed size, which is called as your context vector. Now, once encoder converts a plain word, a simple English word, into a vector, context vector, that means into a word embedding, that word embedding is then fed into your decoder. It is then fed into the decoder. So the decoder takes the context vector and generates the output sequence. Okay, it generates the output sequence. Sounds very trivial. This is the main architecture, but please remember that your context vector here is a fixed length one. Okay. And मेरा कॉफी तो पूरा ठंडा हो गया. And one important thing is x0, x1, x2, ये सारे individual words थे. Okay, they were all individual words. They have been converted into word embedding form and then they have been taken in the hidden state. Okay, and on this hidden state itself, your decoder network works and gives you some output. Now we don't know whether the output is actually matching your input or not. We don't know whether your output matches your input. Means if I say, how are you in English? There are three words, how, are, and you. But in Hindi, it simply says, kaise hain. There are two words, kaise and hain. Okay. So two words need to come. Three words the, yahan two words ban gaye. Okay. Again, order mein aana chahiye. Decoder needs to give you in order. तो decoder का क्या है scene? It does not have any connection with encoder. Means उसको पता नहीं है कि encoder क्या है. It only works on the hidden state, which is a fixed length vector. Okay. So let's see what is this context vector. So encoder, I said, takes the entire input sequence, encodes it into a single vector that is context, using your RNN or LSTM or GRU. Okay. And the decoder starts with the context vector and generates the output sequence. Each step of the decoder, it predicts one token in the output. Okay, one token in the output. And it is completely based, the output is completely based on the previous hidden state and the context. Okay, so now what is a context vector? Context vector, it encapsulates the meaning of the input sentence. That is what I just now had mentioned. एक word अगर ले लिया तो उसका क्या connection है बाकी words के साथ, ठीक है, और क्या meaning infer करता है, ठीक है, that is what is entirely inside that context vector. So it has the meaning of the input sequence in a fixed size vector, regardless of how much big the input sequence is. ठीक है, how much big the input sequence is. Unfortunately, क्या होता है कि since we are fixing the size of the context vector, since the context vector size is fixed, there are chances that we will lose some important information from the input, because input is of variable length, correct? वो सारा का सारा variable length input, we are trying to fix it into a, we are trying to embed it into a fixed size vector, correct? So there are chances that we will lose some important information. So उसको कैसे deal करेंगे? Like how will we deal with this fixed size vector? So this is how your expanded form looks like. X1 is fed inside RNN, ठीक है? X2 is also fed, X3 is also done the same. इसमें से सारा कुछ club करके, let me go to the pointer mode. All the outputs are clubbed together and we form a context vector or the encoder vector. और इसी के ऊपर अभी RNN, individual RNN feed करके we get our output. Now, machine translation example ये है, like I am a student, I want to convert it into French. So after encoding, I get these values, okay, from the encoder. This is the context vector values. And these values are fed inside the decoder. And the decoder's job is to translate it into French. Okay, now some of the applications of encoder-decoder models are text summarization, speech recognition, convert spoken audio into written text, and image captioning. Okay, so now what is the problem with the encoder decoder problem, encoder decoder model is that fixed length context vector. Because क्या होता है कि long input sequences होने से उसको हम we are trying to compress it into like one fixed length context vector, right? So there are chances that we will be losing important information from that input sequence. Okay. So in machine translation, the context vector must encapsulate the meaning of a sentence. Like for example, the quick brown fox jumps over the lazy dog. So if the vector is too small or the sentence is too large, then keywords like fox or lazy dog, they might be misrepresented or ignored during the translation. Now, how do we solve this problem, fixed length wala problem? How we solve it is by using the attention mechanism. Okay, we incorporate the attention mechanism, which helps the decoder to look at the different parts of the input sequence along with the decoding part, along with decoding. So, abhi tak, sorry, what we were doing so far is decoder was only concentrating on this part, that is the context vector. Now, what decoder is doing is along with concentrating on context vector, it is also going back to the encoder part and checking whether this word matches this particular vector or not. That is compares. It is doing a comparison. Okay. So attention mechanism allows the decoder to look at different parts of the input sequence dynamically during decoding. So decoding के साथ वो ये भी check कर रहा है. Decoder is also checking whether this whatever I've decoded, does it really match the input sequence? Does it match it or not? Okay. And this is done selectively. That is selectively focusing on the relevant parts of the input. Okay, relevant parts of the input. And obviously it improves the performance. Now, how does this selective focusing works? I'll tell you that in the coming slides. So attention is just that, not just only look at the context vector. Input को भी देखो तुम, ठीक है? Input सही से translate हो रहा है या नहीं? Okay. So attention is rather than relying on a single context vector, the decoder dynamically attends to different parts of the input sequence at each step. That is, at each step, the decoder assigns different weights to each hidden state of the encoder. Okay, focusing on relevant parts of the input sequence for generating the next token. And attention here greatly improves performance for long sequences. Now, how does this actually work? That means, how does the decoder assign different weights to each and every hidden state? Is by using something called as query, key, and value components. Your attention mechanism works in this form. Where is it? Yeah. Your attention mechanism, it has three vectors called as query, key, and value. Okay, and it using these three components itself, it calculates something called as attention score. Okay, so let's see what each and every component means. So the first is query vector. The query vector, it represents the element of interest or the context that you want to obtain information about. Means एक word हो गया या फिर what they call one context हो गया, उसके ऊपर हमें information चाहिए. So the thing is, query basically indicates the entity in question. Okay, the entity in question, and it is derived from the current position in the input sequence. Okay, current position in the input sequence. And the query vector is usually determined by the similarity or relevance between the context and the other elements in the input sequence. Okay, that is one word, how is it related to the other words, like the current word in question. Okay, how much what they call relevance does it have with the other words in the input sequence? And these other words are called as your key vectors. These other words are called as your key vectors. So what are key vectors now? Key vectors are like the query vector, but it is the projection of the input data and is associated with each element in the input sequence. And they are used to compute how relevant each word in the input sequence is to the query. That means how are other words related to the current word in question. Okay. And this relevance is often calculated using the dot product or by calculating the cosine similarity between the query word and the keyword. That's what I called as co-occurrence matrix. Okay, one word, how is it related to the other words in the sentence? Next, and the last one is value vector. Value vector क्या करता है? The value vector is a projection of the input data and is associated with the what they call each element in the input sequence. And the value vectors, they store the actual information that will be used to update the representation of the query. That means ये query means query and key क्या कर रहे हैं? Query tells you this is the word. Key tells you this is the relationship between the query word and the rest of the words. इन दोनों को join करके जो information आता है, that is what we call as value vector. These are called as the value vectors. That is, these values are weighed by the attention scores computed from the query key interaction. How is query word related to rest of the words? That is query plus key information interaction. That is what is represented in the value vector. Okay. So the value vectors are used to determine how much each element contributes to the final output. Okay. So the attention scores, they are nothing but the dot product between the query and each key. Okay. That means it determines how relevant each word in any English sentence, like for example, English I want to convert it into French. Okay. Okay, so that is what I'm trying to calculate using attention scores, means how much relevance we have. So the attention scores computed based on the query and key are used to weight the value vectors, means इस value vector को ज़्यादा importance देना है या कम importance देना है. Higher attention scores mean that the corresponding values are more important for the output. And this is how your attention mechanism works. Means attention mechanism works mainly based on calculations of your attention scores. Okay, more the attention scores, higher the value they will have when considered to the output. Okay. And this is how attention mechanism in encoder decoder model, that is transformer model, looks like. I just want to have a sister And if you notice the solid lines, they are what they call uh, being trained, or they are being checked with individual words, okay, in the corresponding translation. So I is first checked with the sh and all that, okay. And this is the actual mechanism where in attention layer you're calculating the attention scores. So ये attention scores के साथ साथ ये decoder अभी काम करेगा. Earlier सिर्फ encoder decoder में ये component नहीं था, but अभी attention mechanism में क्या कर रहे हैं? We are adding this attention scores and performing the task. So from attention, now let's go on to the transformers. So transformers were actually introduced in what they call 2017. The paper's title was "Attention is All You Need," and they eliminate RNN completely. माने वो sequence to sequence लेने की कोई जरूरत है ही नहीं. Like step by step एक के बाद एक लेते थे. So here attention, say we have graduated to self attention. ठीक है, सेल्फ अटेंशन में क्या हो रहा है, like instead of only focusing, decoder was focusing on context vector along with the attention score given by the attention score given for each input sequence, each word in the input sequence. उसके साथ साथ अभी क्या कर रहा है कि decoder also is checking. अच्छा, attention score आ गया, context vector आ गया, but is this the actual sequence? इसी sequence में आना है या फिर sequence बदलना है? I mean, is this word coming? Is this word supposed to come after so and so word? ये सारा कुछ जो होता है self attention में होता है. Like, is the word correctly fitted into the position or not? So instead of focusing only on the relationship between input and output sequences, transformers use self-attention to model relationship between all parts of the input sequence at once. Okay. They do it like, am I connected with this word? Am I connected with this word? Am I connected with that word? All of them I'm checking in the self-attention part. Okay. And self-attention, instead of doing one word with multiple words sequentially, means पहले मैं check कर रही हूँ if I'm connected with this word. Again, मैं check कर रही हूँ if I'm connected with that word. That way, instead of doing like that, if there are multiple words, okay, if there are multiple words in the sentence, all of them are parallelly being checked with the rest of the words. All of them are parallelly being checked with the translated words. And this is what we call as multi-head attention. That means I am one attention. Next to me, whichever word is there, that will be one attention. Next to that word, whichever other word is there, that will be one head. So each of us are checking parallelly. Am I connected with this? Along with me, the next word, that is also checking if that is connected with this word, this word, this word. All of them are happening parallelly. Okay, instead of one at a time, now we are doing sequentially, all at a time. Okay, parallelly. So this is what we call as multi-head attention. Okay, instead of using single attention mechanism, transformers use multiple attention heads to capture different relationships between tokens, and each head focuses on different aspects of the sequence. Now, along with this, as I mentioned, decoder also needs to check whether the word after translation is being put in the correct position or not. That means if I say, how are you? Then that is in Hindi, kaise hai. You can't write hai kaise, right? Kaise, ठीक है, उसके बाद ही है follow होगा. So है कहाँ पे रखना है? Okay. That is decided by something called as positional encoding. That is decided by something called as positional encoding technique. That is, since transformers don't have a built-in sequence model like RNNs, we use positional encoding. That means to define or tell the position कि भैया इस word के बाद ये word आना चाहिए. I mean, this is the order. Okay. फर्स्ट ऑफ ऑल हमने वर्ड्स सबको वर्ड एम्बेडिंग्स में कन्वर्ट कर दिया, ट्रांसफॉर्मर ने सब वर्ड्स को कन्वर्ट कर दिया, फाइन. बट इसमें मेजर प्रॉब्लम ये है, वी डोंट नो द ऑर्डर ऑफ टोकन्स और ऑर्डर ऑफ दिस वर्ड एम्बेडिंग्स. इनको ऑर्डर में रखने के लिए वी यूज समथिंग कॉल्ड एज पोजिशनल एनकोडिंग. तो अभी क्या है कि along with the word embedding, we also will be adding positional encoding vector. Okay, वो मैं दिखाऊंगी. I'll show you how positional encoding is calculated. So this is the main architecture. Word embedding यहाँ से चले गया. इसके साथ साथ addition positional encoding भी दे रहे हैं. That is, if it's a even position or odd position in the sentence, ठीक है, उसके ऊपर multi head attention डाल दिया. एडिशन ऑफ द लेयर्स एंड बैच नॉर्मलाइजेशन कर रहे हैं, ठीक है. फिर ये फीड फॉरवर्ड हो रहा है, ठीक है. फ्रॉम देयर यू आर अगेन adding and normalizing, because all the adding तब होता है when we have some dropout layers. उन सबका हमें ऐड करना पड़ता है, आउटपुट सारे ऐड करने पड़ते हैं और उसको नॉर्मलाइज करना पड़ता है, which we are doing using batch normalization. And the same goes here for for what they call the decoding part. outputs कैसे generate कर रहे हैं, and at the end हम softmax activation function we'll be using, because multiple words होते हैं, we have to give them various outputs, various probabilities. तो इस चक्कर में we use multi class है, तो that's why we are using softmax function. and ये थोड़ा elaborated है, ठीक है. जहाँ पे हमने decoder भी डाल दिया है, encoder and encoder 1 and encoder 2, और यहाँ पे है हमारा decoder और decoder 1 and decoder 2. और like just now I had mentioned, वो attention scores हम कैसे calculate करते हैं using query, key and value. और this is how your encoder self attention looks like. Means उसको हमने encoder 1, encoder number 1 और encoder number 2 को और elaborate कर दिया, and this is how it looks like. Attention scores are first calculated for each and every word. Okay. उसके बाद हम उसे देते हैं और फीड फॉरवर्ड न्यूरल नेटवर्क में डाल के फिर प्रोबेबिलिटीज कैलकुलेट करेंगे. और मल्टीपल हेड कैसे वर्क करता है. सपोज वी हैव अ सेंटेंस, द कैट सैट ऑन द मैट. One attention head may focus on understanding subject-object relation, that is cat, mat. Another might work on sat, mat, etc. ठीक है. तो ऐसे करके हम different things parallelly words को chunks में divide करके, and we will be trying to find out the relationship between the input and the output sequence. Okay, this is how your multi-head attention looks like. And coming to the positional encoding, each position in the sequence is assigned a unique coding. That means based on the position in which they are. Okay, and the position encoding is calculated using sine and cosine functions. And positional encodings are added with the word embeddings. Okay, so in the sentence, the cat sat, positional encoding ensures the model knows that the word the comes before cat. and before sat. तो ऐसे I mean ये sequence कहाँ पे वो word आना चाहिए? That sequence में correct position of the word is given using positional encoding. And these are the equations. Positional encoding for even position, we use sign function. And for odd function, we use, for odd position, we use cosine function. Okay, so word embedding के साथ साथ हम positional encoding भी देंगे. Please remember this because coding में अभी जब हम code करेंगे तो ये करेंगे जरूर. Now coming to the last part, BERT. So BERT का full form है bidirectional encoder representations from transformers. So let me go back to LSTM. LSTM में when we had worked, if you notice, we actually worked in a feed forward manner. माने feed forward in the sense हमने context को analyze किया था, based on the context हमने output दे दिया था. But क्या होता है sometimes कि वो सारा sequence में ही था. Sometimes what happens is we can't perform the training based on one word at a time. We need to understand or we need to extract information or meaningful information from the context all at a time. Everything needs to be collected at a time only in order to get the output. Okay, in order to get the output from the context. In order to do this, we have taken by LSTM. By LSTM, what happens is we go in the backward direction. Processing happens forward as well as backward, left to right to left, both at a time. Okay. And that is it happens left to right and right to left all at a time. And everything is done at a time. That is what your BERT does. That's why it's called as bidirectional. That is the first point. Then the second point is, along with the bidirectional characteristic of LSTM, it is also using another characteristic from the transformers, which is encoder. Encoder, what was happening in case of encoder of transformers? एक ये था कि encoder was converting into word vector. दूसरा ये था कि we had incorporated self-attention. We had also incorporated multi-head attention. Along with the multi-head attention, we also added positional encoding. ये 3 features जो encoder part में थे, transformers के encoder part में थे, they are added along with the bidirectional LSTM. That is the reason why it is called as bidirectional encoder representations from transformers. ठीक है, एक तो LSTM को bidirectional कर दिया, back and forth का, फिर हमने एनकोडर का जो वो एडिशनल माने एडवांस्ड वर्जन था वो सारा कुछ इसके साथ ऐड कर दिया एंड now it has become BERT. Okay, so that's why that's how the name comes for the BERT. So why it matters? The bidirectional approach allows BERT to capture the full context of the words at a time. Okay, and this can be used in LLM. That's how your LLM actually works. It takes all the context at a time. But unfortunately, एक problem है LLM के साथ. अगर आप long sequences दोगे, then it will start forgetting. वो problem अभी भी है. So now let's see how the what they call BERT model works. In BERT, there are only 2 operations. One is called as masked language modeling. I mean, BERT only can do two operations. One is called as masked language modeling, and the other one is called as next sentence prediction. Okay. And in case of masked language modeling, for both these things, MLM and NSP, to work, you require a pre-trained BERT मॉडल माने आपके पास ऑलरेडी एक एग्जिस्टिंग कॉर्पस होना चाहिए जिसके ऊपर आपने एक एनएलपी मॉडल ट्रेन किया हुआ है मींस यू रिक्वायर ऑलरेडी pre-trained model which comprises of a corpus ठीक है which is trained on a corpus fine now let's see what this masked language model does BERT is a pre-trained model, okay, which tries to predict a word which is masked in a sentence, which is masked in a sentence. For example, the cat sat on the dash. Dash is masked, okay, it is masked. And your BERT needs to predict the correct word under the mask. Your BERT needs to predict the correct word. Correct word means the word which has the highest probability. Okay. Okay. For this masked word. And the highest probability is mapped. Abhi, how do we know that the word is mapped? How can we know that the correct word is mapped? We know it because we already have a pre-trained model with us. We know it because we already have a pre-trained model with us. Now the same goes with next sentence prediction. In case of next sentence prediction, what BERT does is it tries to find out relationship between consecutive sentences. That is given two sentences. BERT predicts if the second sentence logically follows the first one or not. Okay. If I'm continuously talking since past 2 hours on RNN, and if I suddenly shift and start talking about CNN, that means RNN is logically nowhere related to my flow with CNN, right? If I have to talk another half an hour about RNN, so RNN and CNN are nowhere related. If I talk continuously for another half an hour about RNN, then that means logically RNN, what I was talking for 1.5 hours earlier, and what I'm going to talk now are both logically related to each other. And this logical relationship, that is, if one sentence follows another sentence logically, is given by a Boolean value. Okay. The cat sat on the mat. The cat drank the milk. Both of these are logically related to each other. So if there is a logical relationship, the Boolean value will be 1. The cat sat on the mat. The dog ran away from the house. These two are nowhere logically related, then they will be indicated by a 0. Boolean value for those two sentences will be indicated by a 0. And how do we come to know the relationship, whether these are two related, actually related to each other? By using the pre-trained model. Okay. So for your BERT to work properly, you require a pre-trained model. And on this pre-trained model, we get our actual output or the desired output by performing fine tuning. Okay, we perform something called as fine tuning. Now, for any given sentence, if we want to perform masked language model, या फिर next sentence prediction, we need to add 2 tokens. One is called as CLS, other one is called as SEP. CLS and SEP. Those things will be automatically added if we are using BERT. CLS basically indicates classification. Okay, it indicates classification. वो मास्क लैंग्वेज मॉडल जो है उसके लिए आपको क्लासिफिकेशन करने के लिए आई मीन क्लासिफिकेशन टोकन ऐड करना जरूरी है. ओके, एंड सेपरेशन SEP stands for separation, which is for your NSP, that is next sentence prediction. That means one sentence उसके बाद separation token अगर आएगा, the next sentence is the next sentence in the sequence. Okay, so these two tokens will automatically be added with your BERT what they call BERT input, and along with this you would be adding your positional embedding. They will be converted. Along with that you will be adding your segment embedding, token embeddings, because your BERT now converts it into word embeddings and token embeddings form. And then you perform your BERT modeling on it, and at the end you would be generating the output tokens. Okay, and this is how your masked language model looks like. How are Dash doing today? So the possible outputs that you would be having are you, they, your, etc. The one with the highest probability, okay, that will be selected under this masked language. I mean, sorry, this masked word. Okay, so the probable word would be you itself. Fine. So this is how your BERT model works. And in order to work on BERT, you need to have a pre-trained model. First and foremost is BERT is trained on a large corpus, okay, using masked language and next sentence prediction. And for a specific task, like for example, text classification or question answering or sentiment analysis, कुछ भी आप specific task ले लो, all we will be doing is fine tuning the pre-trained model. Okay, we will be fine tuning the pre-trained model. For example, fine tuned BERT on sentiment classification can classify what they call sentences into positive or negative, give the reviews of a movie. Tomorrow one movie is going to get, tomorrow nahi, 5th ko, which movie? That Pushpa 2. Here in Andhra, Telangana, Pushpa 2 is going to be released. So उसका अगर review करना है, you can use BERT model, fine-tuned BERT model to do it. Okay. And this is the fine-tuning, how it is done. You have 110 million parameters for the base BERT model. Out of them, you should be using 340 million parameters. What they call, if you have a BERT larger size model. And bidirectional context, that is pre-trained model is itself called as your transfer learning. And the BERT model is itself used inside your LLMs, be it ChatGPT, be it Llama, be it Claude or anything. The basis for all these large language models is your BERT itself. Okay, and BERT, it works on bidirectional, it incorporates bidirectional LSTM, works on masked language modeling and next sentence prediction. Those are the only two functions which your BERT can do. Along with that, it has a positional encoding. It has multi-headed attention, that is parallelizing or giving attention scores parallelly to each and every word. Okay, all of these are combined inside your BERT, and whatever what they call modifications are being done or trying to improvise LLMs are nothing but improvising BERT itself. So with this, we have completed our lecture on the text analytics part, the theoretical aspect of text analytics. And these are some of the application, question answering, sentiment analysis, etc. Okay, and text classification. So we have completed now the theoretical part. Now let me okay. Now let me go to the coding part. Is this code visible to all?
Yes, ma'am, it is visible.
अच्छा, अभी हम क्या करेंगे कि पहले we will see how RNN works. What I'll do is I'll briefly describe because एक एक चीज को अभी क्या नाम है decode करके बताने में it will take me a very long time. So we'll start off with RNN, then we'll discuss encoder, decoder. Then we will talk about self-attention mechanism in transformers. उसके बाद we will talk about multi-head attention कैसे देते हैं. Then multi-head attention के साथ positional encoding कैसे करते हैं. And the last we will discuss is BERT. ठीक है. All these we will be dealing using application of text analytics. Fine.
Yes, ma'am.
अच्छा. So the first is like हमने libraries import कर ली हैं. And as I mentioned in the beginning, RNN क्या करता है कि simple अच्छा. So these codes, अच्छा, let me mention before कि these codes are what they call written by my student, PhD student. And that's why he's sitting here कि अगर मैं कहीं गलती ना कर दूं तो he will help me out correcting my mistake. ठीक है, but hopefully I won't do that. So the first is like we import all the libraries from the TensorFlow. Okay, and the first idea is like we take the text to be hello, convert the text into characters, each text into characters, and then give them indices. Like I mentioned in the beginning that we are converting each and every letter or each and every word into one hot encoding. Here we only have one word, so what we have done is divided them into characters and then given them, converted them into something called as indices. Okay. So the character set is nothing but whatever. Just a second. Who is that? Ask him to come after. Come after half an hour, please. Give it there. Just a second, please. Total 35 undali. अच्छा, ठीक है. Sorry for that. We are like completely busy with paper correction, doctoral scrutiny reports and all since morning till night 7 o'clock. We are all been busy with that, and nothing can wait. No one can wait for me. That's the problem. Even in the morning, I was delayed. Fine. So where was I? I was saying that first we convert the normal word into individual character and give them into what they call feed them into indices, convert them into indices, and then what we do is we map each and every index with an individual character. So that's what this char to index and index to char does. Next is we convert all the text into numerical format and give it variable names like input data and character data, because whatever input sequence we are giving, we need to get the output, target output also. Our target output here is ELLO, and the input data that we are taking is HELL. Okay, we have removed last word O. So input will be HELL. Output, please remember, it is ELLO. वही हमें चाहिए, बट यहाँ क्या करेगा, सीक्वेंस टू सीक्वेंस लेगा, एक के बाद एक, वन वर्ड. पहले y1 will be y1 needs to give output as h, y2's output should be e, y3's output should be l, and like that. Outputs that we should need to get is y1 e, y2 l, y3 l, y4 o. This is our correct output which we need to get. Okay. So as I mentioned earlier, one hot encode kar diya for each and every input output, because the computer understands that only, bits and pieces. So we converted all of them into zeros and ones form. Okay, added batch normalization. We need to do the normalizing also. Defined the RNN model. Okay, and added the Adam optimizer to it, trained it over 100 epochs, then generated the data, okay, because we need to again convert it, okay, and for a given length, that is vector length, if you remember, we need to predict the words, okay, and that generated, that is given as your generated text. So your generated text needs to give us the actual target, which is ELLO. The rest of is like the entire conversion prediction of the model and giving them the scores. So let's run it. Already हमने run किया था, but यहाँ पे we are running it again. So if you notice, इसको क्या हो गया अभी? Where it is invalid to 63 line number. Why did it come? I don't understand. So far what it has generated is H, L, O, L, O, so on and so forth. First iteration में ये हमें आया after 100 epochs. Now again when I run it, it will give me one more output. We need to keep computing this over 1,000, 10,000 epochs until we get ELLO. Okay, so that is the RNN. This is the problem with RNN. कि 10,000 करेंगे, 1 lakh epochs करेंगे, कितना भी करेंगे, पता नहीं है. We don't know at after how many time steps we would be getting ELLO as our desired output, right? So that is the main problem with your RNN. It goes in a sequence. It takes a lot of time to compute or get the desired output. Hence, we resort to encoder-decoder model. Okay, now where did this disappear? Yeah, yeah. Now, in case of encoder, decoder, what did we do? We first said that we will first encode the words, okay? And then the decoder will take the normal, what they call, decoder will take it from the context vector. अभी उसको हमने क्या किया है कि input is this text, that is numbers, and the task is we need to give the words, concerned words. One digit word, and digit 1 is represented as ONE, digit 2 is represented as TWO, and this /T basically indicates it is start of the token. Okay, start of the token. Now, input words are now converted into, we need to convert it into context vector, if you remember, right? These context vectors are taken as what they call input underscore vocab. Input underscore vocab. That is your context vector. Okay. And the target token index, that means the target vector jo aayega hame, that is converted or taken as output vocab. Okay, that is converted as output vocab. So the input which will be going inside decoder, the input which will be going for decoder is nothing but your input vocab. Okay, input vocab. And reverse mapping, that is decoding it. Okay, that is done using these functions. Yeah, using these functions. Input underscore token back one by one. Fine. And this is the combination or combining encoder decoder together, because if you remember, we had combined there also in the architecture encoder to context vector, that is hidden state, and from hidden state to the decoder. Okay, so this is the entire architecture for that. So we are using decoder LSTM, defining the model, okay, compiling it, that means running it, training it, and then decoders, what would be the output from the decoder? That's what is happening in this part. Okay, and of course you would be having the dense layers and all that, which goes into the decoder as well as into the encoder part also conversion. Okay, and the text that we are trying to give, the output that we are trying to get. So let's run this. The output is 1, 2, etc., and the predicted would be the words. Sorry.
This encoder decoder is also similar to the RNN. We are using the RNN again, something like LSTM, which is having the sequence. It's not a bidirectional level, but the main thing here is we are having a center point called context vector. We are trying to convert the input data into a vector and then decode it with the same tokens. It is converted into a vector with the name of tokens, and using those tokens, we are reversing those tokens back to the output. So you will have, see, if you see the outputs like OFF, AFF, it is just understanding the classes of it. See, if you see HUTT are coming, FF are coming, if you are checking for the predicted one, it is repetitive, right? It is just understanding the class of it. I mean, like if it is 1, 2, 3, 4, for everything it is saying like, it don't know the value. I mean, it doesn't know if it is numerical digit 1 is going to enter it into it. It is just converted into a token. So upon the token, we are just trying to decode it. So it only knows the class, whether it is F class or T class, F class or T class. So it is just thinking that I just want to print it only the class, but not the text. So it's just printing the class for us.
Yeah, and this is the main drawback that we have with the plain encoder decoder, because we are not checking the input sequence. We don't have the input sequence. We are just decoding it. Okay, digit 1 can be F, digit 1 can be O, like if you notice here. Okay, it can be T in some other part. See, like if you can notice here, it's T, T, T. It's not focusing on the input. So for this itself, now let's add the self-attention mechanism. Yeah, In case of self-attention mechanism, I mentioned to you earlier also that we are adding something called as attention scores, right? So these are called as raw attention scores, and then we put them into scaled attention, means in the sense we are normalizing those attention scores. Okay, so that's what we have just added. Like, these are the words that we are taking as input, converting them into word embeddings. Okay, and then what they call, where is the attention score? This is the this is the attention score that we are calculating. And as I mentioned, we are using Q, K, and T. T mane is nothing but that value which we are taking. Okay. And then we are scaling them, okay, and printing them based on the scores. Means what are the attention scores given to each and every word in the sentence. That is what this particular code is doing. So what we are doing is printing the attention weights. Okay, that is after applying the softmax function, because softmax will give you the highest probability of the words. Means जिसका highest probability होता है वही ऊपर आएगा. So these are the word embeddings. Raw attention scores, scaled attention, then attention weights, that means highest jiska aaya, wo sare inside we are giving after softmax, and softmax is giving you the weighted sum of the values. Means after adding all the probability values, whichever is the highest, that will be predicted as your output. Okay, it's only giving you attention scores here. Okay. Now this is only for a single word to the rest of the words in the sentence. That means one word, how is it related to the rest of the words in the sentence? Now we need to do multi-headed. Mane, how many, given a particular set of words, we are performing multiple, what they call attentions. Okay. And that is done using number of heads. Means how many heads do you want to keep parallelly. So I'm taking 2 heads. 2 words will be simultaneously checked with the other heads. So first it will be the cat, next will be cat sat, or maybe sat on, etc. 2 words at a time. Okay, so that's what this particular code is doing, multi-head attention. Which one should I? Yeah. I just now terminated. No, let me close this. Okay. Now let's run it. Is anyone feeling hungry in the class? Yes, no, neutral. Is anyone there who's feeling hungry in the class?
No, ma'am.
Hey? Acha. Acha. So step 1 is compute the, step 1 is split the data into QKV. Okay, and step 2 is compute the attention scores based on Q and K values. Scale them again, then apply softmax function, okay, attention rates, and split them, output split, and then combine all of them together, like जो 2 multiple heads, 2 heads लिए थे, उन सबका हमने अभी combine किया है. ठीक है? So just a second. Yeah. So the final output after combining all the multiple heads is this. Now to this we are adding the positional embedding. Positional embedding mein what we did is we added these two functions extra. Means sine function is added for even indices and cos function is added for odd positions in the sequence. And where did we add it? Yeah. This is how we converted positional encoding. And we added this somewhere. Just a second. Let me show it to you. Where did I add? Where did I add? Oh yeah, दिख नहीं रहा. Yeah, the input, okay, with positional encoding is word embedding of each word along with positional encoding. Okay. Now these two are fed into QKV and let's run it. And as I mentioned, positional encoding हम क्यों कर रहे हैं to find the actual position of the word in the sequence. Multi-headed attention आ गया along with the sequence. Okay. So this is with the positional encoding part. Okay. Now the last part is BERT. BERT क्या करता है? दो चीज करता है. One is masked language करेगा और उसके साथ या फिर it will perform next sentence prediction. So first is we divide all the words into something called as tokens. ठीक है? Hello, how are you doing? This is divided into tokens and converted. One of the words will be masked. Okay, let's run it. So the token IDs are these for that sentence and the attention mask is this. Okay. Next is, as I mentioned, pre-trained word for, we are performing some text this thing. I love programming. I hate bugs in the code. Okay. So this is what we would be converting. Yeah. So the probabilities that we have got from this model are these values. And then for the classification part. And these are the CLS embeddings that we are getting. Okay. Yeah, you want to add? Yeah. The classification part is only done. Next sentence prediction, we didn't add that into this. Okay, this is only for checking whether given, I mean, whether we are able to perform by LSTM part in this BERT model or not. So this we have completed the so-called hands-on session. Of course, इतना hands-on तो नहीं था, but as much as possible, I tried to give you the hands-on session. So with this, I've completed my lecture and done with the text analytics part. Yeah.
Thank you, ma'am. Can we get these code files for sharing among?
Sure, I'll send it across. Hi, Sarita.
Thank